Now we're going to talk about diagonalization. Before I get into that, I want to go over change of basis. We talked about this earlier. I recommend you go back and see the video on linear transformations to refresh your memory. So the picture is we have a vector space V and a basis V1 through Vn. Then if we have a linear transformation from V to V, you have the matrix of that linear transformation, A, I meant to say T, a matrix with respect to this basis. The matrix depends on the basis. And what you do is you, for the ith column, you put the coordinates of T applied to Vi, and by coordinates I mean the coordinates with respect to this basis. So that is to say, you write it like this. Okay, so that's the notion of the matrix with respect to a basis. Now, we talk a lot about the usual basis, E1 through En, and we generally don't mention it. And we have the usual notion of the matrix of a linear transformation. So what we're going to talk about is the following. Suppose I have a linear transformation, and I give it as a matrix with respect to the usual basis. But now I have a new basis, V1 through Vn. How do I find the matrix of T with respect to this new basis? And I'm sorry, I mixed up A and T again. It's the matrix of T with respect to this basis. Well, the answer is the following. We make up this new matrix S, where you put the vectors V1 through Vn as columns, and then the matrix of this linear transformation in the new basis is S inverse AS. Okay, so that's kind of interesting. Why is that? Let's see. Why is that? So, what is the meaning of this S? Well, what S does is it takes a vector in the basis of the EIs, the usual basis, and it hands you a vector, the same vector, in the other basis. That is to say, S goes this way and S inverse goes the other way. So, for example, what do I mean by that? Where does S take the vector 1 and a bunch of zeros? Well, if you multiply this matrix by this vector, you get the vector V1, and that is to say, the vector V1 in the standard basis. So here's the conclusion. If you have a matrix in one basis, the matrix in the new basis is given by S inverse AS. And let's see why that is. So we'll do an example. What is, if you take this new matrix B and apply it to V1, what do you get? Well, suppose V1 is written this way in the usual basis, A1, E1 up to AN, EN. So this S, that's the first column of S, is this A1 through AN. All right, so now let's look at what B does. It takes the vector V1. Well, it's the vector V1 in the basis of the VIs, which is to say a 1 and a bunch of zeros. And then S takes it to this thing, which is that vector in the standard basis. And then if you apply the matrix A to it, what do you get? Well, since A is with respect to the standard basis, you get A applied to V1 in the basis of the EIs, and then you just apply S inverse again to get you back this vector in the basis of the VIs. So that's how this works. You change basis twice. You go once in one direction and once in the other with A in the middle. And if you look at these operations in order, you're applying S and then A and then S inverse, and so the matrix is S inverse A times S. Okay, so that was some general nonsense. Now let's talk about this in the setting of eigenvectors. So suppose we have an n by n matrix, and let's suppose that it has n linearly independent eigenvectors. That's not necessarily true, but suppose it does. So that is to say, you have a vector v1 with eigenvalue lambda 1 and so on, vn, and eigenvalue lambda n. What is the matrix of this linear transformation with respect to this new basis, the basis of vi's? Well, it's obvious. A v1 is equal to lambda 1 v1, and so on. So that just says that in this basis, it's the diagonal matrix, lambda 1 down to lambda n. So that is to say, if I make this matrix S the way I did before, S inverse AS is equal to this diagonal matrix. So here's the conclusion. If you make this matrix of eigenvectors, then S inverse AS is diagonal. And a key point is that this works if v1 through vn are linearly independent, because then S is invertible, which of course you need to be able to do this. All right, time for an example. Take this 2 by 2 matrix with ones on the off diagonal. What are its eigenvalues? Well, you compute the determinant of this matrix and you get lambda squared minus 1. So it has eigenvalues plus or minus 1. And it's easy to see, you do a little calculation, that the vector 1, 1 is the 1 eigenvector, and the vector minus 1, 1 is a minus 1 eigenvector. Okay, I just confirmed that with this little calculation. All right, so let's make the the matrix S. We put V1 in the first column and V2 in the second. And you compute S inverse. What's that? Well, it's 1, 1 on the diagonal and looks like this. And the determinant is 2, so you have to stick in this plus a half. So let's compute S inverse AS. Just write it down. It's 1/2 this matrix followed by A followed by S. And if you just do the calculation, let's see, multiply the second two matrices together to get this, and then multiply these two matrices together, and what do you get? You get a 1, 0, and let's see, a 0 and a minus 1. Okay. I think it's worth looking at our previous discussion in this example. Let's take the vector 1, 0, and this is in the new basis. So what happens when we apply S inverse AS to it? This first column here gives you 1, 1, and then you apply A, and since this is the one eigenvector, it takes it to itself, and then S inverse takes you back to 1, 0. So this shows how this operation takes 1, 1, the eigenvector 1, 1 in the old basis, to the eigenvector 1, 0 in the new basis. Okay, so the point here is that it's nice to diagonalize a matrix. I've mentioned this before, diagonal matrices are the easiest matrices to understand, and by diagonalize I mean find a basis, v1 through vn, consisting of eigenvectors. So that is to say, if you make this S as before, you do this operation and you turn A into a diagonal matrix. And you say A is diagonalizable if this is possible. Well, so there's an obvious question. How do you tell? When is it possible to diagonalize a given matrix A? So there's a basic fact, which is, suppose you have a bunch of eigenvectors, v1 through vm, with their corresponding eigenvalues, not necessarily n of them, just some number m. And suppose that the lambda i's are all distinct. Then there's a very nice fact, which is the vi's are guaranteed to be linearly independent. Eigenvectors with distinct eigenvalues are linearly independent. Okay, so from that you conclude the following theorem. Suppose A is an n by n matrix, and suppose A has n distinct eigenvalues. Well, then A is diagonalizable. Well, that's because these n eigenvectors are guaranteed to be linearly independent, so they give you a basis. So I should emphasize an obvious fact here, and it's the following. A matrix A is diagonalizable. To say it's diagonalizable is exactly the same thing as saying that there is a basis consisting of eigenvectors of A. And these eigenvectors, these eigenvalues might or might not be distinct. I'm not addressing that issue. And I say this is an obvious fact. Why? Well, because it is obvious. What does it mean to say that A is diagonalizable? Well, it says that in some basis you can put it in this form, and, well, that basis is exactly the basis of eigenvectors. So now suppose we have a matrix A and it does not have n distinct eigenvalues. I'd like to examine whether it's diagonalizable or how you can tell. So, well, here's an example. Take this matrix. This has only two eigenvalues, 3 and -1. You say that the 3 is repeated. So this matrix is diagonalizable. Well, it's tautologically diagonalizable. It's already diagonal, even though it doesn't have n distinct eigenvalues. So it's not necessary to have n distinct eigenvalues for something to be diagonalizable. And here's the key example. Take this matrix, 1, 1, 0, 1. And let's ask, is this diagonalizable? Well, let's compute its eigenvalues. You do this computation. 1 minus lambda squared. There's only one eigenvalue, which is 1. So it's not guaranteed to be diagonalizable by the theorem. Well, so we have to check. Can you find a basis of eigenvectors? That's what I was saying. It means for it to be diagonalizable. So we better go ahead and compute what the eigenvectors are. So, well, we all know how to do that. We have this matrix, and it only has one eigenvalue, so we're looking for the one eigenvectors. So you take this thing and you plug in lambda is equal to 1 to get this matrix, and we're talking about the null space of this matrix. Well, let's just compute it. You check whether this applied to xy is 0, and, well, you better have y is equal to 0. That is to say, the null space is exactly the matrices where the second coordinate is 0. This is a one-dimensional space. It's spanned by the vector 1, 0. And so obviously there is not a basis consisting of one eigenvectors, because the one eigenspace is only one and not two-dimensional. So therefore, this matrix is definitely not diagonalizable. And this is kind of the prototypical example of a non-diagonalizable matrix. I think it's kind of nice to see this another way, which in some ways is easier, maybe easier to remember. Suppose this matrix was diagonalizable, or is diagonalizable. That would mean that S inverse AS is diagonal. Well, diagonal what? It's the eigenvalues are on the diagonal, which would be 1s. So if you bring the s's to the other side, this would say that A is S times the identity times S inverse. But the identity just goes away, and this forces A to be the identity. So since our matrix is not the identity, it's not diagonalizable. Okay, so I want to look a little bit at this operation, taking a matrix to diagonalizing a matrix. So one important observation is that when you do this, the determinant of A is the product of the eigenvalues. Well, that's because if you bring the s's to the other side, you've written as A is equal to S diagonal matrix S inverse. And when you take the determinant, the determinants of S and S inverse cancel, and you get lambda 1 through lambda n. So replacing a matrix by S inverse S times itself doesn't change the determinant. So in particular, you notice that A, we've talked about this before, A is invertible if and only if 0 is not an eigenvalue. That's an elementary statement. And suppose A has eigenvalues lambda 1 through lambda m, and m is possibly less than n, the dimension of the space. Then another condition for A being diagonalizable is that it better be that if you add up the dimensions of all the different eigenspaces, that they add up to n. That's the thing which failed in this example of a non-diagonalizable matrix. All right, I want to conclude with an application, computing powers and eigenvalues of powers. Suppose A is a diagonalizable matrix with eigenvalues lambda 1 through lambda n. I'd like you to tell me what the eigenvalues of the power of A are. A to the k, if you multiply it times itself k times. Can you tell me what the eigenvalues of this product are? Well, let's see. If A itself was diagonal, it would be obvious. If you take a diagonal matrix and raise it to a power, you just get the powers on the diagonal. So you take the eigenvalues and raise them to the k. But what if A isn't literally diagonal, just diagonalizable? So that would say that S inverse AS is equal to such a matrix. Well, notice that if you take S inverse AS and take the power of that and raise it to the k, well, as I said, that's lambda 1 to the k through lambda n to the k. On the other hand, if you just literally multiply this thing out by itself k times, you get this, and all of these intermediate s's cancel, and what you get is S inverse times A to the k times S, which is to say that the diagonalization of A to the k is this matrix lambda 1 to the k through lambda n to the k. Okay, so the conclusion is A to the k, this is a misprint, A to the k has eigenvalues lambda 1 to the k through lambda n to the k.